All right. I normally do not ask you to do things in order on the playlist because we're here to just practice problems, but this is number 2 in the Physics and Calculus 1 problem set, and I'm going to increasingly get more difficult. So if you did not watch the first one, which is a real blow-through that doesn't even really come to any specific answers, please go back and have a look at that one. I'll link it in the description. And if not that, the explainer video as we're just moving into it. So we are going to be using derivatives to solve real physical problems. And this being number 2, it's going to be a pretty easy one, but I think you got to start with easy and then ramp up the pain, right? So let's just look at what we've got here. It's just like in the explainer video and in number 1. There's a ball that's being thrown vertically upward, and then what's it going to do? It's going to come back down. When would it ever not do that, right? And I'm looking at it over time here, but really it's actually moving straight up and down according to this. It's just up and down like this. That if you look at it as a snapshot of time, it would look like a parabola, wouldn't it? So I'll put a t here. And we'll just say that this is the height, which they call s in this problem for some reason. That's common in physics to see weird variables doing things, so we'll just go with it. And they even give us a formula, s equals negative 16t squared plus 80t. I highly recommend writing it in power order like this. And the one thing you want to remember is this is going to be your acceleration factor. This is going to be your velocity factor. And I know that immediately because a t squared means that the original unit is going to be in like meters per second squared, so that when you multiply by seconds squared, it cancels and you end up with a distance. And we're calculating distances. And the other one for velocity would be meters per second. So you're going to multiply by time one time to end up with a distance measure. That's just kind of a secret way to look at this and understand. Here's my gravity and here's my velocity. Both of them contribute to distance together, but it's important to remember from the explainer video, here, acceleration creates velocity, and velocity creates distance. So while acceleration is creating velocity and velocity is creating distance at the same time, this equation factors both of them in together as time passes by. So what do they actually want from us? They want to know the maximum height of the ball. And if you remember from the other videos, how do we find that out? Well, at the top, the velocity was going up, and later the velocity is going down. This is the moment where the velocity is 0. It has a slope of 0. Velocity is the slope of distance, so the slope here should be exactly 0, where velocity is 0. Let's take the derivative of distance, right? I'll call it d dt because we're talking about what happens over time, and we have time as our functional input here, and that'll give us velocity. And that's going to be power rule, negative 32t plus 80. You should understand that. If we set velocity to 0, then that's going to mean that's just out of the way, and we'll say 32t equals 80. And for t, we're going to get looks like 2.5. I want to say 2.5 seconds. So that tells us that the 2.5 second mark is right when you get to this top here. Pretty simple. Yeah, we don't know how high it is yet, but if you wanted to, you could put 2.5 in right here and find the height. They're asking what's the maximum height reached by the ball. We should calculate that, don't you think? I'm plugging 2.5 into this and I get 100. That's what I got for my answer. But I went fast. Still, that should be the answer to part A. And then part B says, what is the velocity of the ball when it's 96 feet above the ground on its way up? So they're saying somewhere here at 96, there's one spot here and there's one spot here, and they want to know the velocity at each one of these. Well, in order to figure that out, we need to know where this is, and that means we're going to need the time factor for that. Well, let's start with that. I'm going to put into the original equation 96 equals negative 16t squared plus 80t. In fact, let's move the 96 over, and I'm just going to make this 0. I should have just erased it. Whatever. And then I'm going to divide out. Can I divide a 16 out of everything? That would be nice. 96 divided by 16 I think is 6, so we should be okay. Let's divide by 16 and we get negative t squared. plus, what is it? 5t minus 6, I think. And I don't like to FOIL with a negative powered polynomial. So let's times by -1 on everything. We'll call it t squared minus 5t plus 6 equals 0. And I can factor this. Remember factoring from algebra? Most of my calculus students fail because they're bad at algebra, not because they can't understand the more advanced stuff. That should be a -2 and a -3. They add up to make -5, and they multiply to make +6. I believe this is correct. So that means to make a 0, we'll have a t is equal to 2 or 3. And that makes sense because when I look at this, here's 2, and here's 3 seconds. So at the top, it was at 2.5 seconds. Wouldn't it make sense to you that half a second ahead and half a second behind both determined the same height? It should have a symmetry like this to you. You should see this and be like, that makes sense. And now that we have the time factor, what do they want? What's the velocity? Well, we have this formula. So just plug in 2 and 3, and I think, I don't know, I think I can just do it in my head, right? That would be, the first one's +16, the next one's -16. Those are the two answers here. Because again, this going down should reflect what it looked like when it was going up this way, 16 positive and 16 negative. It's not like the energy entered or exited the system, so we should see this balancing metric here. But the thing to understand is, when you have a distance formula, if you take the derivative, you've got velocity. And between the two, you can figure out the time of things, and you can figure out the height and velocity of things when comparing them to each other. So take this in stride, and let's go on to number 3.